Good day, everyone, and welcome to another interesting session of this webinar series by leading IEEE Electron Device Luminaries, which is jointly organized by the IEEE Electron Device Society Delhi chapter, New Delhi, India, along with the Department of Biotechnology Star College Program at the Upadhyaya College, University of Delhi, and the National Academy of Sciences, India, Delhi chapter. The National Academy of Sciences India is the oldest science academy in India, established in 1932. Today we have with us Professor Songmo Steve Kang, who is a distinguished professor emeritus and distinguished research professor at the University of California, Santa Cruz. And he'll be talking to us today on the topic evolution of semiconductor technology. He's a well-known figure in EDS and is currently Distinguished Chair Professor Emeritus and Distinguished Research Professor at the Baskin School of Engineering, University of California, and is also the Chancellor Emeritus of the University of California, Merced, and President Emeritus of KAIST. He has published over 500 journal and conference papers, over 10 books, including a textbook on CMOS digital IC analysis and design that has been translated into multiple languages and used globally, and holds 16 patents too. Before returning to academia in 1985, he led the development of world's premier fully CMOS 32-bit VLSI microprocessor chipsets for telecommunication and computing applications as a technical supervisor at AT&T Bell Labs. He has received honors including the Silicon Valley Engineering Hall of Fame Induction, Alexander von Humboldt Senior U.S. Scientist Award, IEEE Millennium Medal, IEEE Mac van Valkenburg Circuits and System Society Award, IEEE KAIST Society Technical Excellence Award, U.S. Semiconductor Research Corporation Technical Excellence Award, IEEE Leon K Graduate Teaching Technical Field Award, IEEE KAIST Society John Trauma Education Award, and the Chang-Lin Education Leadership Award. He is a recipient of the 2023 IEEE KAIST Society Darlington Best Paper Award, and he has received his Ph.D. degree from Fairleigh Dickinson University, New Jersey in 1970, honorary BS degree from the Yonsei University, MS degree from the State University of New York in 1972, and he got his Ph.D. degree from the University of California in 1975. He is a life fellow of IEEE, a fellow of the Association for Computing Machinery and the American Association for the Advancement of Science, a life member of the Korean Academy of Science and Technology, and a foreign member of the National Academy of Engineering, Korea. His current research interest includes neuromorphic computing, low-power VLSI circuits and systems, and emerging technologies for heterogeneous system integration. So we welcome Professor Kang, and this whole webinar series is part of an IEEE Electron Device Society's initiative to celebrate the 75th anniversary of the transistor invention. With these words, I now invite Professor Kang to kindly share his screen to deliver his talk.
Thank you for your kind introduction. Let me see how slide mode. Yes, I would like to give my talk on the semiconductor technology with emphasis on innovative evolution, starting from the primitive integrated circuit consisting of even single transistor, 4 transistors, all the way to transistors. So there is a new book called for most critical technology. That is semiconductor technology based on MOS transistors and other innovative devices. So I like to give you a brief outline of my talk. So what are the really challenges for engineers in the 21st century? And then brief overview of semiconductor technology from single transistor to VLSI chips. And lastly, systems view. How can you apply these innovative devices and circuits and systems for daily applications such as AI, machine learning, and even brain scale neuromorphic computing. So looking into 21st century engineering challenges, there are many. As we all know, with the global warming, emphasis on renewable energy and the clean environment, health is always a concern. Nowadays, security, not only defense, military type of security, but cyber security. What is a highlight in the box is reverse engineer the brain. Why so? Well, discovering the secrets of how living brains work may offer the best guide to engineering artificial intelligence, AI, in a larger scale. So reverse engineering the brain promises great advances in healthcare, manufacturing, and communication. And lastly, there are also important role for scientific tools. So this shows where semiconductor electronics play important role in today's cyber physical world, starting from cloud computing, neuromorphic computing, analog computation, sensor everywhere, and scientific tools including JWST telescope, medical devices, and then the robotics, UAV, drones, traffic control, and CCD imaging, and even solar energy, smart grid, and LED lighting, which has a tremendous impact on saving energy and the power, and then communications. So it's all over. But let's look into the briefly. You are quite familiar with this history by now, but today's emphasis is on the transistor invention in 1947, right? So as of last year was a 75th anniversary. So that was the invention of a transistor to replace the vacuum tube. And then comes the invention of integrated circuit, which I would like to highlight in my talk by Jack Kilby and Bob Noyce. But equally important is Duan Kang's metal oxide semiconductor transistor, first fabrication back in 1960. And without maybe MOS transistor, we would not have today's VLSI technology. So this, again, highlighting 75th anniversary of a transistor invention, which was a germanium bipolar junction transistor. There's a good book. If you are interested in, I would recommend very highly this classical book called Crystal Fire, written by Michael Riordan and Lillian Hodgson, The Invention of a Transistor and the Birth of an Information Age. And it's a very well written and quite exciting book. And you can see all the background, what they have gone through to come up with the first transistor. This shows the beginning of Silicon Valley. What you see, this gentleman is William Shockley, who was in the team of a transistor invention. He came out in 1956 to establish a Shockley Semiconductor Lab in Mountain View, California. So that is a sort of a historical picture. And the day after, the Fairchild was born. Unfortunately, Dr. Shockley was not a good manager, so people came out to have a Fairchild. And then soon after that, this Intel, Gordon Moore and Bob Noyce founded Intel Corporation back in 1968. Following year, my friend J.D. Sanders, he's an Illinois graduate, that's how I know him. In 1969, he founded AMD Corporation. And today, both Intel and the AMD, they are major players in this VLSI technology. These inventions were significant enough to earn Nobel Prize in 1956 for invention of a 1947 transistor invention. And then back in 1958, first integrated circuit, one germanium transistor, one capacitor, three resistor, was achieved by Jack Kilby at TI 1958, for which he got Nobel Prize in year 2000. Now, this is something that I like to highlight. Jack Kilby, who died, this is wrong. He died he died in 2005. I'm sorry. This picture that you see here was taken in September 15, 2000. At that time, I was a department head of Illinois Electrical and Computer Engineering Department.
Professor Kang, your slides are not changing. We are still at slide 2.
Is that right?
Yes.
I'm so sorry. Why is that so? My slide is changing.
No, maybe if you can share your screen again, and if you can try. Yeah, now it's changing. Now we are at slide 4.
Sorry. I'm sorry. So, okay, so let me see. This is a slide number, right? So I talked about grand challenges, the cyber physical world, semiconductor electronics, and then history of transistor invention and integrated circuit. And this is anniversary of a transistor invention, and the book on crystal fire by Michael Riordan and Lillian Hardison. And this is the beginning of a Silicon Valley, William Shockley Semiconductor Lab, Fairchild, and then thereafter Intel and the AMD. This is a Nobel Prize recognition, year 1956 for invention of a transistor, 2000 for invention of an integrated circuit. Now this is what I am going to emphasize, the importance of a IC revolution, right? So what you see here is a picture taken on September 15, year 2000. That time I was a department head of a University of Illinois at Urbana-Champaign. And Jack Kilby was our distinguished alumnus. So we gave that recognition on September 15. We didn't know that he would get Nobel Prize. So on October 15, exactly a month later, Nobel Prize was announced. And then on December 8, 2000, he received the Nobel Prize. And in his acceptance speech, here, this is what I like to highlight. In 1958, my goals were simple: to lower the cost, this I underline, especially cost, simplify the assembly, right? That's what the integrated circuit does, and make things smaller, of course. Yeah, we want to minimize physical size and more reliability. You had a lecture on the MOS reliability, but reliability is very, very important. So that's the essence of the VLSI technology: lower the cost, simplify the assembly. In my opinion, integrated circuit is like a packaging in a sense. So that simplifies the assembly process. And then transistors are smaller, interconnections are shorter, and then reliability is also achieved. Many reliability issues in electronics comes from the contacts in interconnects. So although I do not consider myself responsible for all the activity that has followed, it has been very satisfying to watch the IC's evolution. I'm pleased to have had even a small part in turn the potential of human creativity into practical reality. Earlier, we talked about the younger generation people not appreciating as much the contribution of a hardware and semiconductor technology, more toward leaning more toward the software and other management type of roles. But really, the turning human creativity into practical reality was achieved through invention of an integrated circuit. Imagine what we would do without integrated circuit. We wouldn't have a cell phone, for instance. So the hardware technology is important, and it's not going to end today. There will be new kind of hardware with innovation down the road. So the equally important was the Bob Noyce, the invention of an integrated circuit, which was about 6 months later, 1959. All components on silicon IC, including copper wires. That's important. Yeah, he included wires. And then fully monolithic, using planar process developed by Oni. And then while Kilby's integrated circuits germanium, his really integrated circuit including the interconnect. Kilby's interconnect was using external wires. So Bob Noyce made as much the contribution. Had he lived, he would have shared Nobel Prize. But in order to get Nobel Prize, you have to be alive. So that was the history. Earlier, I mentioned the important contribution of MOS transistor. Back in 1960, Duan Kang and his boss, Martin Atalla at Bell Labs, they made the first MOS transistor. This shows the drawing, hand drawing of MOS transistor structure. This shows a fabricated device, but it has a silicon substrate, a silicon dioxide, the thermally grown dioxide, and then aluminum metal gate. So that's why metal oxide semiconductor MOS device. This shows, this is drawing and then cross-sectional cut of a device and then IV characteristics. If you are not familiar with the integrated circuit as a device engineer, it is illustrated in this inverter logic gate. That is sort of a most basic circuit element in VLSI, which consists of NMOS transistor, PMOS transistor connected, joined in the drain, also has a sharing the input and then output. So when input is high, output is low. When input is low, output is high. When input is high, output is low again. And this is a transition, switching from high to low, switching from low to high. And the cross-sectional picture is shown here. And then, we are familiar with the DRAM, which consists of one NMOS transistor with a capacitor. We are also familiar with the SRAM, which consists of typically 6 transistors, 2 inverters back to back, and test transistors, and the bit line and the bit line bar, for instance. So that's fundamental, the elements in integrated circuit. And today we have a big market for DRAM as well as SRAM, right? Now, the progress, evolution of an integrated circuit followed the Moore's law by Gordon Moore, who just passed away recently. Back in 1965, he introduced Moore's law, which predicts the future of integrated circuit. That time he was a Fairchild's director of R&D. He predicted the rate of increase of a transistor density on an integrated circuit would double every year and later double every 2 years. And this is the initial curve that he plotted. And then the 10 years later, updated 1975, and then this trend has been continued. So indeed, this prediction has played an immense role, because whenever engineers faced a roadblock and couldn't do it, they said, how can it be? According to Gordon Moore, this should happen. And they innovatively found the breakthroughs and continued the mission. This shows first 4-bit microprocessor chip, 10 microns PMOS, back in 1971 by Intel Corporation, contained 2,300 transistors. And thereafter, a lot of progress has been made to increase integrated circuit size, the LSI and then VLSI. But in order to design integrated circuit, you have to rely on SPICE. This is a SPICE is a simulation program with the IC emphasis, so SPICE. And this shows the history of SPICE. In case you didn't hear about it, was born at UC Berkeley in EECS department back in early 1970s. Gentleman you see on the left-hand side is Ronald Rohrer. He's a Berkeley graduate. He was a young assistant professor at Berkeley, also worked at the Fairchild. And when he was teaching a course, he asked students in his course, will you take a final exam or will you develop simulation program? And he's notorious for imposing difficult problems in the exam. So students chose to do software development and developed what is called the CANCER, computer analysis of a nonlinear circuit. So that's why CAN circuit. So CANCER. So then one of the students in the class was Larry Nagel, shown on the right-hand side, Lawrence Nagel. And then a gentleman in the middle, you probably know him, he's Donald Peterson. So Ron Rohrer, he decided to leave Berkeley and then talk to his senior professor, Donald Peterson, will you take over this program? And the condition was when you give this program out to industry, you should charge because it's a valuable program. And Donald, he said, no, I wouldn't charge any. And then there was a conversation back and forth. Finally, he had to yield to Don Peterson to give out free. And that caused the huge success in integrated circuit because the industry appreciated this SPICE program and marched on. Without this SPICE program or descendants of that program in industry, such as Cadence tool or Synopsys tool, you cannot do integrated circuit development. So that's a very interesting story. And also Don Peterson, as a supervisor of the Larry Nagel, he made sure that models are correct. So he forced Larry to design circuit, fabricate it, measure it, compare with the simulation result to make sure that the simulation is correct. So that's a very, very important development. Equally important was the Dr. Herman Gummer at AT&T Bell Labs. You know that he's well known for Gummel-Pun model for bipolar junction transistor, but he introduced a bunch of CAD tools at AT&T Bell Labs. And many members of Bell Labs moved to Silicon Valley to participate in Salomon Design Automation Company, which became Cadence, for instance. But he lived through year 2022. This is what Larry says, Nagel, once he was a member of Herman Gummer's department at AT&T Bell Labs. I often wonder to myself how somebody so brilliant so successful, could be so humble. We will miss Herman, but his achievements are woven into the fabric of our electronic design automation tools, and we will never forget Herman. That's what Larry Nagel said. And I have known Herman at AT&T Bell Labs, and was difficult to work for Herman Gummer, so brilliant. So he has many good ideas. So he will assign some project to people, and often even before they start the project, he would have solved it. So that's how brilliant he was. So that's Dr. Herman Gummer. We miss him dearly. This is the microprocessor development at AT&T Bell Labs I was involved in. So I started actually 5-micron technology, and then this chip was designed using 3.5 micron CMOS technology. We call the Belmec 80, because supposed to come out in 1980. Supposed to be the second generations of Belmec 8-bit microprocessor, that's named 80. And this shows first fabrication success. The US postage stamp, 8 cents, was made in celebration of this the Belmec 80 chip. But this was not very successful because of long wires. So I emphasize all these rows that you see, the black rows, they are standard cell rows. And then in between is wires, and it became very, very lengthy. Wires became very lengthy, and thus speed wouldn't come out. So we had to redo this in next generation 2.5 micron CMOS technology we call Belmec 32. This shows the layout of a Belmec 32 with many, many improvements in terms of wire management and a more compact layout. And it was a huge success. Target was 6.2 megahertz, but even run at 8 megahertz, 9 megahertz, because the interconnect was much shorter. But even with the advancement of the CAD tools, CAD tool couldn't handle this verification of the chip. So we had to generate this huge Calcom plot. Maybe about more than 60 pieces. We scotch taped them together to create a 20 feet by 20 feet Calcom plot. And then we had to check all the interconnects with a color pencil by tracing on line and so on. This shows the part of the team in front of Alexander Graham Bell statue in AT&T Bell Labs, Murray Hill. So that was an interesting story. When it came out, IEEE Micro declared the Belmec 32A was a champion in terms of its performance and technological success. So other team, HP, and then Intel and the National Semiconductor, yeah, they also developed the microprocessor chip, but it was not as powerful. We also owe a great deal to Robert Denard at IBM. He was brilliant. He was one inventor of a DRAM chip, but equally importantly, he introduced what is called the scaling law. How do you do the scaling of integrated circuit technology? All the device scaling, wire scaling, and then performance and so on. So that's a huge contribution of Denard at IBM, the Yorktown Heights. This shows the picture taken in January 2023 for 3 nanometer technology, gate all around device using 3 nanometer technology. So how does Moore's law plays? Well, if you look at, say, over 50-year period, if you assume 2x improvement every 2 years, so the improvement over 50 years would be almost 34 million in terms of packing density. In 1972, 10 micron technology, Intel 8008 chip had 3,500 transistors. In 2022, If you multiply 34 million to 3,500, it will be about 117 billion transistors. NVIDIA GPU chip 2022 had 80 billion. It's pretty close, actually, not bad, even less than factor of 2. How did it happen? Well, innovation involved the photolithography. J. Lathrop, when he was at TI, he patented in 1957. Now we have extreme ultraviolet photolithography of ASML and other companies. So there are a lot of components in manufacturing of an integrated circuit, right? The other one is all this the distortion problem in photolithography, but that was solved by mathematicians. This shows what is called the application of an inverse mapping principle in mathematics to mask generation. So when you have a mask like that, when you process, it doesn't come up like this. It's all distorted. So instead, you distort this mask to create this type of a pattern. So that's essentially the inverse mapping principle in mask generation. This was done by the information theoreticians at Stanford University. So it was not even IC device engineers or IC technology people. Essentially they applied mathematics to resolve this problem. Tom Kyler was a professor and he's a graduate student. They created a technology company, numerical technology, which was very successful and effective. Now, this shows the importance of VLSI, in particular, the making it smaller, making it cooler with less power dissipation, and increasing the performance. So in VLSI, the smaller, the cooler, the better, for instance. So in terms of a VLSI figure of merit, you want to achieve a high packing density. So density goes on top. You want to reduce power, so it goes bottom. You want to increase the speed, the delay goes up on the bottom. So essentially, you have 1 over energy, area, or volume. For instance, so if you make cooler, the energy is less. If you make the smaller, area is less, or even 3D volume is less. Then figure of merit goes up. The picture illustrates the importance of power dissipation. That's where a lot of attention is paid on low power design. Practically, you can fry the egg on top of a printed circuit board when it dissipates so much power. This shows the destroy of a package due to high power dissipation. So that's why the smaller, the cooler, the better. This shows a microprocessor trend since 1970. And if you look at it with the importance of power, you don't want to exceed 100 watt per chip. So that's why there is a sort of a flattening, because you don't want to exceed that much power. And as a result, a lot of things are happening. Although transistor count is increasing, in terms of architecture, so they do, multi-core type of a parallel architecture type of a thing. So that's another innovation. This shows innovation starting from material system all the way to architecture. So the conventional architecture may be von Neumann and the multi-core, but in terms of architecture, it's moving toward the neuromorphic computing because it's a lot of parallel processing, low power. In terms of a state variable all the way down, in terms of a charge, that's what we are relying on in typical design. Like DRAM is charging capacitor up, or it is charging down. So electric charge, but that is becoming less reliable. So tend to move to resistance as a state variable. So that's what I want to next emphasize. How can you do neuromorphic computing using resistance as a variable, for instance? This shows the person who coined the term neuromorphic computing. His cover made the professor emeritus at Caltech. Now he's in Silicon Valley. For his great contribution, he got Kyoto Prize in year 2022. Yes, a brilliant person. So let's look into the AI and machine learning. So as you all know, AI has become very, very popular, especially with the ChatGPT and the other type of things. And although this is a trend of the Moore's law, when you look into AI, the increase is double every 3.4 months. The Moore's law is doubling every 2 years, but the AI application, AI computing need is doubling every 3.4 months. It's tremendous. So how can you solve this problem without hardware innovation? That's where we need more innovative devices, more innovative circuit, more innovative system to address this sort of issues. So when you look into reverse engineering human brain, there are hundreds of, trillions of billions of neurons, 3-4 orders of increase in number of synapses that connect to neurons. That's like interconnects in integrated circuit. And then total surface area is like a handkerchief size, 2,400 square centimeter. So if you pull out your handkerchief and then lay it flat, that's sort of roughly the surface area of a human brain. Now, related to that is Merced technology. Leon Chua was my graduate advisor when I was a graduate student. I joined his group in 1972. But in 1971, he published a paper in Transactions and Circuit Theory, Merced, the missing circuit element. So if you look into this chart, the quadrature structure, there's a resistor, inductor, and the capacitor. But this has been linked, missing. That's why it's a missing circuit element, which is an element that relates between charge and the flux directly. Right, directly. And if you look into the IV-Lisage figure, for instance, when you have a two-terminal device, apply voltage, and then current comes out. If it's a resistor, it's a single line passing through origin, right? If it's a linear, it's a straight line passing through origin. If it's a capacitor or inductor, it will be like an oval figure. Inductor figure and the capacitor figure. Merced is quite unique. It has a number 8 figure. It passed through origin and then has a hysteresis like this. So that's a distinctive nature of Merced. Missing link between charge and the flux. It has a pinched hysteric loops like shown here, pinched here at origin. And has a sort of a memory effect that's called the memory resistor, so memristor. So that's what is coined as a memristor. So I joined his group in 1972. By the time I graduate, we published a paper called Memristive Devices and Systems in 1976 to generalize this memristor concept. This shows how you do it. So if you have a relationship between charge and the flux, some nonlinear function, it's not obvious physically, but if you take a derivative, time derivative on both sides, you can see that it's a V voltage, time derivative of flux is a voltage, and then memristor times current. So that's why it's called memristor. It has been quiet since then, but back in 2008, Stan Williams and his group published a paper in Nature called yeah, we found membristors. We fabricated membristors. So it reproduced all these membristor characteristics, 8 figure. And then as the frequency increased, this the width of the loop decreased, it becomes almost a straight line. And this shows a number of publications since 2008 in terms of citation grew almost exponentially. Yeah, this was updated in 2017, more than 30,000. And today is even far more than that. This shows first memristor fabrication, platinum plate line, nanowire, another platinum wire here, and in between is a titanium dioxide, TiO2 here, and that's where state variable plays. So as you apply flux or voltage here, with the time, the width of the oxide layer, reduced oxide layer changes. So that's a WS state variable. And you can explain this one. Voltage is equal to function of W as a state variable. So this is a membristance. Membristance depends on the width of this reduced oxide layer in the device, for instance. And then this Ronald Wasser at in Germany, he published a paper called the classification of memristive devices. So he shows the redox-based switching phenomena device in a red area, but all the other devices, nanomechanical memory, phase change memory, thermochemical effect, all this ferroelectric tunneling, magneto-resistive memory effect, he termed them all they are memristive in nature. And this shows spin transfer torque MRAM. This is a structure, but if you model it, it becomes a memristive device. It's a voltage is equal to resistance multiplied by current, but the state variable is also here. It's a memristive device. Now, the nice thing about memristive device, memristor, is you can tune this memristor resistance up and down. So it's applicable for reconfigurable electronics. So if you have an analog circuit, if you want to tune the resistance in the circuit, you don't have to replace it. You use a memristor and you program it, programmable. So this shows the programmable voltage controlled amplifier. You use memristor here, and you can program the resistance, and its gain can change up and down. Also, you can use this in neuromorphic circuit, neural network. For instance, you have the weight, and you can program the weight just like this. So that's another application. So next, the application to neuromorphic computing using memristor, for instance. Why neuromorphic computing? Well, brain is the golden standard in terms of energy efficiency. So we trying to mimic the biological neural network using the neural network, the hardware neural network. So if you look at a neural network or compared to neuronal circuit, it has many inputs. So you have many inputs. You have neurons, right? Neurons with the weight. So the weight, resistance, another way, and that there is some threshold function here, and then activate to generate another neuronal signal to propagate next stage and so on. So that's the thing here. If you look into the neuron itself or synapses that connects the neurons, it turns out both are memristive. This shows that synapses are memristive. So it has been experimentally shown that this memristor behave just like a synapses and a biological network. If you look into neuron, which generates action potential, this shows Hodgkin-Huxley equation for which they got Nobel Prize in physiology medicine. This is a Hodgkin-Huxley model. It's a stiff nonlinear differential equation. Has the two channels, sodium and potassium channel. And when you look at this, we jointly with Leon, we looked into this. We declared that this is a memristive in 1976 paper. This is a memristive, and this is a memristive, for instance. So you can say that neuron can be realized using memristors. Synapse can be realized using memristors. So now brain is consisting of neurons and synapses. So what about looking into possibility of having solid state brain using memristors, for instance? So that may be crazy idea, but it poses an interesting question. So this shows what is called the crossbar array. So you have a matrix structure in between. You put memristors. So by applying voltage biasing, you can program all these different weights. This shows some matrix structure of this device, crossbar array. This shows how you can implement memristor in a CMOS circuit. So you have a MOS structure here. This is a MOS gate, source drain, right? And then this is an interconnect. Vertically, you can put memristor here on top. And this is a device structure. So that's very nice, actually. It's a CMOS compatible. This shows how can you do analog computation. So this shows a crossbar array with a memristors. So you multiprocess, and then you have a current sum of a currents, which is like here, input data, neuronal weight, so synapse weight, and then output equation, just like this circuit here. So that's analog computation. And we indicated that if you have this sort of array, you can realize it very, very compactly because it's a nanostructure. So density will be very high, right? So here, the area is very small. So the value goes up, figure of merit goes up. Furthermore, we recently published a paper, how to build the MIF, memristive integrated fire, spiking neuronal signal generation. So we using two off-the-shelf memristor component. If you provide the current pulse, you can generate this neuronal signal. See, it's quite interesting. So this memristor can be used to generate a neuronal signal, for instance. See, there's no other program other than just automatic switching within memristors, depending on the voltage across this capacitor here, for instance. And so you can apply this memristive neuron and the memristive wave for artificial neural network. And we have simulated and then tested against what is called benchmark. There's a bunch of numbers, right, for zip code recognition and so on. And turns out that the accuracy is quite high. It's 93%, for instance. The other benchmark, and with a much less the power consumption, and then we also did a fashion MNIST benchmark and the dynamical video signal, and all performed properly. So it's quite encouraging. So the next question is, well, if so, then can you realize a solid memristor? Well, we can do some exercise. Yeah, we said number of neurons 100 over billions. Synapses is 3-4 orders of magnitude higher. Surface area is 2,400 square centimeter. In terms of volume, is 1,000 cubic centimeter. So if you do memristive brain surface area calculation, it turns out you can realize less than 2,400 square centimeter using 3.5 nanometer feature size. This is not possible using CMOS alone. So that's quite encouraging. This shows some realization of a memristor circuit. So you have it's a power and the signal lines, and then vertical line, and then you have a memristor at the intersection. So that's how you recognize to realize this sort of a thing in this single line structure, for instance. So that indicates the potential. We cannot say we can do it, but at least the potential, interesting, intriguing potential. This shows the 2.6 trillion transistor chip, Cerebras chip, which is a 21 centimeter by 21 centimeter, has 850,000 cores, and this shows a supercomputer, AI supercomputer system in the box. It consumes 23 kilowatt, much better than a megawatt type of thing. And then as a device engineer, you would appreciate if you look into such a chip, 2.6 trillion transistors. But what if you didn't have a device transistor? What if you relied on old vacuum tube, say 12AX7 small vacuum tube, which is a 2 centimeter diameter, 4.5 centimeter height. And if you compare this to Lotte World Power in Korea, 123-story high, 555 meter high, total floor area of 300,000 square centimeter. And if you put all of these vacuum tubes only, you need 40 of these buildings to just store vacuum tubes. In terms of cost, this vacuum tube is almost $20. If you multiply by 12.6 trillion vacuum tubes, is 20 times of Korea GNP, 2 times of US GNP. So that's how the device technology, invention of a transistor contribute to the world economy, for instance. Looking into future, we are interested in building high-value semiconductor system. So if you look to the future, the health industry, biochips application. If you look into the scaling, yes, so now we have 3 nanometer, and then my former student at TSMC says even 1 nanometer would be possible. And on top of that, we have a 3D structure coming up. So there's a lot we can do for the future. The hybrid RM and CMOS chip technology is also encouraging. So the Bayesian circuit with the 2,000 memristors on top of a 30,000 CMOS transistor was done at the University of Paris. And the memristor runs AI task at 1/800th power. So that's tremendous power saving. So it was published in January 2023. So it's quite exciting to see this development. And looking into the future, there's a lot more you can do. You can use a chiplet and advanced packaging technology, neuromorphic computing, a lot of startups, and then even quantum computing, device technology, scaling, and nanosheet device, and other packaging, 3D integration, and so on. And furthermore, at the system level, you can do lots of co-optimization. In all days, people said, oh, problem is complex, you divide and conquer. So you optimize, sort of parts and then assemble them together. But with a supercomputer now, you don't have to. You can put the whole system and then system optimization. And that's a possibility. We mentioned about advanced packaging, 3D integration. Also, you can connect a chip to chip directly with the fibers, optical fibers, right? So this is being developed at many companies, Intel and AMD and so on. So it's quite exciting to have a transistor interconnect, advanced packaging, and system co-optimization. So a lot can be done to further improve the hardware system, for instance. So that's the end of my talk. So I like to encourage, especially younger generation people, to seriously look into getting deeply involved in exciting development of hardware. Software is not all, really. Software cannot run with the energy efficiency without energy efficient hardware. That's where our future is. I think we rely on younger generation, innovative engineers to lead us for future. Thank you.
Thank you very much, Professor Kang, for enlightening us about, right? We have been listening a lot of things about DTCO, so device technology co-optimization, and moving it from device level to the system level, covering all parts of related to the memristor and all kind of devices. So that's really great. And there are a few questions which have been shared by the attendees. Let me just share my screen.
Okay.
Yeah, I hope my screen is visible to you.
Yes.
Yeah, please go ahead.
So let me address that. So maybe from the top to in the absence of efficient CAD tools in the 90s, how did the engineers solve the thermal issues related to density, etc.? So yeah, even back in late 1970s, early 1980s, the reason why Bell Labs so they did it. Now, after that, even CMOS had a high power dissipation. So people talked about how to resolve these thermal issues. And a few decades ago, at the Stanford University, there was a PhD thesis, how you can cool down the chip by introducing micropipes underneath the chip. And then another invention was micro refrigerator on chip. So my colleague Ali Shakri, who is now at Purdue University, he introduced a micro refrigerator on chip, and you can cool down local hotspot area. But even in 1990s, when I was at Illinois, we started introducing a simulation tool. IET Sim is one of them. We included thermal aspect. So transistors are not sitting at the same temperature on chip. Chip on hotspot will the mobility will be much lower compared to not so hotspot and so on. So we incorporated that. Found out that you can have a chip failure actually on chip because of a local hotspot. So we solved that problem using that. So that was a technology transfer. The ESD problem was also due to thermal problems. So we solved that to find out where failure happens on IO frame, that sort of a thing. So that number two, including GA technology, there is a significant toward the vertical integration. How does one thermal dissipation? Yeah, so that's the thing that I mentioned that this is a huge problem, right? So we have to solve it either through the micro pipe type of a cooling or embedding micro refrigerator type of a thing. So that's number two. So you're experts about the NIT and HP India today. Thanks to how modeling spice device circuit level design, no power. Can you take up the yeah, so yes, this is yeah, asking many important questions. So education and the training. So way, if we cannot handle in 4-year program, whether membrane is a composite material based on semiconductor. Yes, so membrane is a titanium dioxide, and there are many more membristors. So this is a very active area of research. So, I do not know all the material systems, but it's ongoing research, number 4. What is your opinion about alternative technology that may have potential to increasing the processing power most complex tasks ever required supercomputing? Yeah, so supercomputing and quantum computing and photonics, optical computing, and all emerging technologies. But for special purpose applications, if one can afford high cost military application and so on, you can do that. But the power consumption is a limitation. So yeah, that will be increasing the challenging, because you cannot have a supercooling for ordinary applications. So that's that. Number 6, signal integrity. Yes, so crosstalk, electron migration. Yeah, this has been ongoing 1980s. We found the signal crossing and so on. So as a side joke, the IC interconnect is like a human interconnect. When people are close, there can be crosstalk, rumors, and that sort of thing. So what do? You put a buffer in the middle, ground wires or power wire. In integrated circuit, you do exactly the same thing. If two signals are clock signals, it will be good to use power ground wiring in between, for instance. And there's lots of simulation tools to monitor crosstalk, electromagnetic interference, etc. So CAD tools are essential to do this sort of thing. Number 7, delay time is a crucial component. Yes, such as membrane through physical diffusion metal. Assume that their operation exceeding slow is membrane response time is than transistor field. Yes, so the interconnect is always the important issue. So that's why the vertically aligning layers is important. Through silicon via type of a thing is important. That's why aluminum is replaced by copper wires and vertical stacking and minimizing. So minimization wire length is critically important. So even back in 1980s, after having failure of the Bell-Mac 80 due to long wires, what we did was the wire-centric design was introduced at that time. This is back in 1980s. So you can think of having the city planning. When you plan a town, what do? You plan the road first, and then you place houses. You don't build the houses here and there, connect them. This is exactly the same when you develop the integrated circuit systems. You worry about the interconnect, and then if the interconnect is long, then driver has to be more efficient. So you do the transistor sizing, that sort of a thing. So yeah, that's number 7. Yeah, thank you.
Yeah, thank you, Professor Kang. I think Professor Rudan has raised his hand. Please go ahead, Professor Rudan.
Yes, I just want to make a comment. In one of the slides, there was a list of achievements by Herbert Gummel, like the Gummel and Poon model. And so I was slow in reading it, so I don't remember whether there was a mention of a numerical scheme that was proposed by Scharfeter and Gummel.
Oh yeah, there are that many. Yes, yeah, thank you for mentioning it. This Herman was he was a genius. So he introduced many novel ideas, many contributions. In fact, when I was working at the Bell Labs, I used to go to Bell Labs early in the morning, but who is there? You guess, Common is there early in the morning. When I leave very late. When I leave, the Herman is still there. I had another colleague who was even worse than I was. His name is Masakazu Shoji, who has 2 PhD, one in Kyoto, one in Minnesota. He was a brilliant engineer, but when he leaves late at night, if anybody is in the lab, he goes back to his desk to leave the last. But Herman was brilliant. He worked so hard. Although he was brilliant, he was the hardest. When he had an accident and he hurt his leg at his hospital bed, people visited him, asked him, "What do you want to do?" And he said, "Bring my laptop," so that he can continue work on his problems. Thank you for mentioning it. It was an inspiration.
Thank you.
Yeah, thank you very much, Professor Deen and Professor Kang, for your kind intervention. And on behalf of the IEEE Electron Device Society, the Delhi chapter, and my other joint organizers for this particular session, I would like to thank Professor Kang for enlightening all of us, and to all the attendees who have been there with us for this particular session. And I extend my invitation to all of you to kindly join us for our future webinars also. Thank you very much.
Thank you. Thank you. Bye-bye.
Bye-bye.